Look, Ma, no hands. I'm holding this umbrella in the wind and rain so it doesn't get on my keyboard, and it buffers the sound, which seems to work. This is the only place I can go now. The other across the street, homeless have taken over the bus stop there and won't let anybody there. Anyway, the blood clotting system, very complex, irretrievably complex. The body commonly stores enzymes, which are proteins that catalyze a chemical reaction, like the cleavage of fibrinogen, which is the one item that's significant in blood clotting. But it has to clot on time and then depart, allowing the blood system to work through without stopping the blood completely. Like the cleavage of fibrinogen, I was saying, in an inactive form for later use. The active forms are called proenzymes. When a signal is received that a certain enzyme is needed, the corresponding proenzyme is activated to give the mature enzyme. As with the conversion of fibrinogen to fibrin, proenzymes are often activated by cutting off a piece of the proenzyme that is blocking a critical area. The strategy is commonly used with digestive systems. Large quantities can be stored as inactive proenzymes, then quickly activated when the next good meal comes along. Amazing design in the human body. Thrombin initially exists as the inactive form prothrombin. Because it is inactive, prothrombin can't cleave fibrinogen, and the animal is saved from death by massive inappropriate clotting. Still, the dilemma of control remains. If fibrinogen and prothrombin were the only proteins in the blood clotting pathway, again, our animal would be in bad shape. When the animal was cut, prothrombin would just float helplessly away by the fibrinogen as the animal bled to death. Because prothrombin cannot cleave fibrinogen to fibrin, something is needed to activate prothrombin. All the materials are there. The system has to act every single time properly, or the species will die. Perhaps the reader can see why the blood clotting system is called a cascade, a system where one component activates another component, which activates a third component, and so on. Now we have a protein called Stuart factor. It cleaves prothrombin, turning it into active thrombin that can then cleave fibrinogen to fibrin to form the blood clot. Unfortunately, as you may have guessed it, if Stuart factor, prothrombin, and fibrinogen were the only blood clotting proteins, then Stuart factor would rapidly trigger the cascade, congealing all the blood of the organism. Again, it's so complex. So Stuart factor also exists in an inactive form that must be first activated. It's like teamwork here. One time it misses and the species dies. Doesn't exist anymore. No accidents. No mutations. This has to be designed. At this point, there's a little twist to our developing chicken and egg scenario. Even activated Stuart factor can't turn on prothrombin. Stuart factor and prothrombin can be mixed in a test tube for longer than it would take a large animal to bleed to death without any noticeable production of thrombin. It turns out that another protein called accelerin is needed to increase the activity of Stuart factor. The dynamic duo, accelerin and activated Stuart factor, cleave the prothrombin fast enough to do the bleeding animal some good. So in this step, we need two separate proteins to activate one proenzyme. Yes, accelerin also initially exists in an inactive form called proaccelerin. And what activates it? Thrombin. But thrombin, as we have seen, is further down the regulatory cascade than proaccelerin. So thrombin regulating the production of accelerin is like having the granddaughter regulate production of the grandmother. Nonetheless, due to a very low rate of cleavage of prothrombin by Stuart factor, it seems there is always a trace of thrombin in the bloodstream. Blood clotting is therefore autocatalytic, because proteins in the cascade accelerate the production of more of the same proteins. Wow, that is so complex. It couldn't have evolved. We need to back up a little at this point, because as it turns out, prothrombin, as it is initially made by the cell, can't be transformed into thrombin even in the presence of activated Stuart factor and accelerin. Prothrombin must first be modified by having 10 specific amino acid residues called glutamate, GLU, residues, changed to gamma carboxyglutamate residues. The modification can be compared to placing a lower jaw onto the upper jaw of a skull. The completed structure can bite and hang on to the bitten object. Without the lower jaw, the skull can't hang on. In the case of prothrombin, GLA residues bite or bond calcium, allowing prothrombin to stick to the surfaces of cells. Only the intact modified calcium prothrombin complex bond to a cell membrane can be cleaved by activated Stuart factor and accelerin to give thrombin. It's such a precision thing, I don't think any human could actually do this. No scientist can recreate this. This has to be created by a super intelligent designer. The modification of prothrombin does not happen by accident. Like virtually all biochemical reactions, it requires catalysis by a specific enzyme. In addition to the enzyme, however, the conversion of glue to GLA, GLU to GLA, it needs another component, vitamin K. Wow, vitamin K is not a protein. Rather, it is a small molecule like the 11-cis-retinol that is necessary for vision. Like a gun that needs bullets, the enzyme that changes glue to GLA needs vitamin K to work. One type of rat poison is based on the role that vitamin K plays in blood coagulation. The synthetic poison called warfarin is made to look like vitamin K to the enzyme that uses it. In the presence of warfarin, the enzyme is unable to modify prothrombin. When rats eat food poisoned with warfarin, prothrombin is neither modified nor cleaved, and the poisoned animals bleed to death. But it still seems we haven't made much progress. Now we have to go back and ask, what activates Stuart factor? It turns out that it can be activated by two different routes, called the intrinsic and the extrinsic pathways. In the intrinsic pathway, all the proteins required for clotting are contained in the blood plasma. In the extrinsic pathway, some clotting proteins occur on cells. Let's first examine the intrinsic pathway. This gets really complicated. The reason why I'm going into it, it gets overwhelmingly confusing and difficult, and all you have to do is just rest in the design of the great creator. Imagine this coming along. If it didn't work, it's going to take trillions of attempts, and mankind would never exist, nor any mammals that have this blood clotting system. When an animal is cut, a protein called Hageman factor sticks to the surface of cells near the wound. Bound Hageman factor is then cleaved by a protein called HMK to yield activated Hageman factor. Immediately, the activated Hageman factor converts another protein called plecalcirin to its active form, calcirin. Calcirin helps HMK speed up the conversion of more Hageman factor to its active form. Activated Hageman factor and HMK then together transform another protein called PTA to its active form. Activated PTA in turn, together with the activated form of another protein called convertin, switch a protein called Christmas factor to its active form. Finally, activated Christmas factor, together with the anti-hemophilic factor, which is itself activated by thrombin in a manner similar to that of proaccelerin, changes Stuart factor to its active form. Boy, you know, I couldn't describe this and take one breath. like the intrinsic pathway, the extrinsic pathway is also a cascade. The extrinsic pathway begins when a protein called proconvertin is turned into convertin by activated Hagemann factor and thrombin. In the presence of another protein tissue factor, convertin changes, Stuart factor, to its thrombin. In the presence the tissue factor, however, only appears on the outside of cells that are usually not in contact with blood. Therefore, only when an injury brings tissue into contact with blood will the extrinsic pathway be initiated. The intrinsic and extrinsic pathways cross over at several points. Hagemann factor activated by the intrinsic pathway can switch on proconvertin of the extrinsic pathway. Convertin can then feed back into the intrinsic pathway to help activated PTA activate Christmas factor. Thrombin itself can trigger both branches of the clotting cascade by activating anti-hemophilic factor, which is required to help activated Christmas factor in the conversion of Stuart factor to its active form, and also by activating proconvertin. Have you gotten all of this? Or you just look to God? Systems must be in place to stop the clotting. So, Behe summarizes, once clotting has begun, what stops it from continuing until all the blood in the animal is solidified? That's a good question. Keep on going and the species will die anyway. Clotting is confined to the site of injury in several ways. First, a plasma protein called antithrombin binds to the active but not the inactive forms of most clotting proteins and inactivates them. Antithrombin is itself relatively inactive, however, until it bonds to a substance called heparin. When it binds to heparin then occurs inside cells undamaged blood vessels. The second way in which the clots are localized is through the action of protein C. After activation by thrombin, protein C destroys accelerin and activated anti-hemophilic factor. Finally, a protein called thrombodulin lines the surfaces of the cell on the inside of blood vessels. Thrombomodulin, binds thrombin, making it less able to cut fibrinogen and simultaneously increasing its ability to activate protein C. So when a blood clot initially forms, it is quite fragile. If the injured area is bumped, the clot can easily be disrupted, and bleeding starts again. To prevent this, the body has a method to strengthen a clot once it has formed. Aggregated fibrin is tied together by an activated protein called FSF, or fibrin stabilizing factor, which forms chemical crosslinks between different fibrin molecules. Eventually, however, the blood clot must be removed after wound healing has progressed. The protein called plasmin acts as a scissors specifically to cut up the fibrin clots. Fortunately, plasmin does not work on fibrinogen. Plasmin can act too quickly, however, on the wound, or the wound wouldn't have sufficient time to heal completely. It therefore occurs initially in an inactive form called plasminogen. Conversion of plasminogen to plasma is catalyzed by a protein called T-PA. There are also other proteins that control clot dissolution, including alpha-2 antiplasmin, which binds to plasmin, preventing it from destroying fibrin clots. That is one big mouthful. Important notes. Behe continues, most importantly, the clotting cascade has to be turned off at some point before the organism completely solidifies and dies. The blood clotting system fits the definition, obviously, of irreducible complexity. Given enough time? No, not enough time. That is, it is a single system composed of several interacting parts that contribute to the basic function, and where the removal of any of the parts causes the system effectively to cease functioning. The function of the blood clotting system is to form a solid barrier at the right time and place that in a place that is able to stop blood flow out of an injured vessel. The components of the system beyond the fork in the pathway are fibrinogen, prothrombin, Stuart factor, and proaccelerin.